Today, we'll be discussing NVIDIA's CosmosWorld Foundation Model, a platform designed to help build AI systems that interact with the physical world. The paper outlines how the platform uses large-scale video data to create digital simulations, enabling safer and more efficient AI training. We'll explore its components, from video tokenization to model fine-tuning, and how it supports applications like robotics and autonomous driving. Now, fair warning, it's a long paper, so this deep dive might stretch a bit too. Feel free to follow me on screen for some light upper body stretches as we go. Let's get started.
Imagine AI systems that don't just think, but also interact with the physical world. Robots with sensors to observe and actuators to move or manipulate objects. These systems could revolutionize how we handle dangerous or tedious tasks, freeing humans from risky jobs. But here's the catch. Training these systems is tricky. You need real-world interaction data, and mistakes during training could lead to serious damage. That's where the World Foundation Model comes in, a digital twin of the physical world that lets us simulate and train AI systems safely. This paper introduces the CosmosWorld Foundation Model Platform, specifically designed for building visual world models. The idea is to pre-train the model on massive data sets, like a 20 million hour video collection, and then fine-tune it for specific tasks. The focus is on handling complex visual dynamics and perturbations, like changes in lighting or object movement. To do this, they curate high-quality video clips using a video language model and leverage hardware-accelerated video processing to scale efficiently. The result? A highly scalable and effective way to train physical AI systems using data pipelines that maximize throughput. Now let's see how the Cosmos platform uses foundation models for physical AI. First, look at the figure here that depicts two main models, a diffusion model and an autoregressive model. The diffusion model excels at producing 3D videos that reflect real-world physics, while the autoregressive model captures the time-based relationships in video sequences. Both of these help in modeling complex 3D environments with diverse, detailed dynamics. After the heavy lifting of pre-training, there's post-training, where these models are adapted for specific tasks. Examples include camera control for precise framing, robotic manipulation for tasks like object handling, and autonomous driving for real-time decision-making in complex scenes. If you glance at the figure, you'll see how each model ensures consistent outputs across different tasks. Detailed driving scenes and manipulation tasks show the depth of these models. This breadth lets the platform scale from simple daily tasks to advanced autonomous systems. Here comes a key idea. Pre-trained World Foundation Models, WFMs, act as broad generalists that learn a wide range of real-world physics and interactions. Check out Figure 2, which shows how these WFMs serve as a base. Then, specialized datasets add task-specific details, creating post-trained WFMs for various physical AI goals, whether it's robotic manipulation, camera control, or self-driving cars. Two pre-training techniques are particularly important. First, diffusion models transform noisy data step by step into clearer video frames. Second, autoregressive models generate each new frame based on the ones before it. These methods leverage cutting-edge transformer architectures to simplify challenging video generation tasks. One big challenge is how to tokenize video data. Videos are packed with details, and you have to compress them while keeping the important stuff. An encoder-decoder setup balances that, preserving key info. Once pre-trained, you can fine-tune these WFMs for very specific goals, whether it's controlling a robot's movements or simulating camera perspectives. Together, pre-training plus fine-tuning offers a scalable, efficient way to advance physical AI. Next, let's discuss the purpose and structure of WFMs. They predict future world states based on past observations and current perturbations. Take a look at Figure 3. You'll see a sequence of previous observations and an input describing a real-world change, maybe a robotic arm movement. The WFM then predicts the world's future state. This allows for complex scenario simulations under safe, controlled conditions. WFMs aren't just for show. They're crucial tools for policy evaluation. Instead of risking damage by testing directly in the real world, you use these digital testbeds. WFMs also help initialize policy models, acting like a blueprint for the environment's dynamic patterns. You can even plug them into reinforcement learning to guide model training, or use them for planning, where you simulate future states to make decisions. In short, they're key to building smarter, safer AI systems. Look at Figure 4, which shows the core components of the Cosmos platform: a video curator, tokenizers, pre-trained WFMs, post-training samples, and a guardrail system to ensure everything remains safe. The video curator chops raw videos into smaller clips and picks only the high-quality, action-packed parts. It then uses a video language model to annotate them, and any redundancies get removed so the dataset stays lean and useful. Next, we have video tokenization. Tokenizers compress videos into smaller, more manageable chunks. They operate causally, which means they process only the current frames and what's come before, just like real-world systems that don't see the future in advance. Finally, we return to pre-training. Diffusion models generate future video states from past frames plus text prompts, while autoregressive models build videos incrementally. These models form the bedrock of WFMs, powering simulations and accurate predictions for diverse physical AI tasks. Now let's focus on fine-tuning WFMs and the pipeline for curating high-quality video data. Fine-tuning includes combining diffusion-based WFMs with autoregressive techniques and using tools like prompt UP samplers to enhance generated videos. This step is all about sharpening model performance for tasks such as robotics or autonomous driving. Figure 5 provides a handy breakdown of the data curation process. It's a 5-step pipeline. First, raw videos get split into segments, then filtering eliminates subpar content. Annotation applies text descriptions, deduplication purges repeats, and sharding organizes clips by resolution and aspect ratio. This way, you end up with a polished, wide-ranging dataset perfect for WFM training. The actual dataset is quite varied, blending proprietary and open-source videos. It spans everything from driving scenes to human activities, even synthetic environments, to make sure the models learn a broad spectrum of real-world and simulated scenarios. Have a look at how diverse and massive the dataset is. It's 20 million hours of raw video, with resolutions from 720p to 4K. Data processing steps weed out duplicates and irrelevant content, preparing both pre-training and fine-tuning sets. Ultimately, this yields over 100 million video clips. Splitting videos into coherent clips is crucial. Each video is segmented at scene changes, ensuring each clip captures consistent context. Tools like PySceneDetect and AutoShotSpot changes using features like color shifts or neural predictions. They also use ShotBench to handle tricky, fast-edited scenes. The result is a more refined dataset for robust training. This section digs deeper into splitting algorithms and transcoding, plus a quick intro to filtering. Check out Table 1 to compare how different algorithms detect shot boundaries. PySceneDetect uses rule-based methods, whereas Transnet V2 and AutoShot use neural networks, which perform better on complex transitions. ShotBench provides a reliable benchmark to compare them fairly. Next, transcoding standardizes these clips into high-quality formats. By experimenting with codecs like H264N and optimizing hardware usage, the team achieves over 6 times speedup in video processing. Filtering comes in last, removing noisy or off-topic clips, so only the best data moves forward into model training. This approach ensures the final dataset stays as helpful as possible. Let's look at more advanced filtering strategies that refine the video data for WFMs. The first is motion filtering, which cuts out videos with no movement or too many abrupt motions. A classifier, using NVIDIA's optical flow, does well here by detecting various camera motions like panning or zooming. Next up, there's visual quality filtering. A model checks for issues like distortion or poor aesthetics. It uses perceptual scores from human ratings and discards the bottom 15%. Text overlay filtering also steps in to remove post-processed text overlays, such as street names in driving videos. Finally, video type filtering adjusts category distributions, giving preference to more relevant categories like human interactions and minimizing the rest. This balanced approach leads to a robust dataset, fine-tuned for practical AI tasks. Here, 3 critical steps: annotation, deduplication, and sharding takes center stage. In annotation, a language model provides captions describing each video clip's visual and narrative elements. The team fine-tunes this model for contextual awareness, and specialized hardware boosts speed dramatically over baseline systems. Deduplication groups similar clips, removing near duplicates and keeping the dataset fresh and compact. Using semantic embeddings and clustering algorithms cuts the training set size by about 30%. Finally, sharding bundles video clips by resolution, aspect ratio, and length. This ensures a smooth match with the training pipeline, making it easier for the model to handle large amounts of data efficiently. Now the spotlight moves to infrastructure and tokenization. On the infrastructure side, they use a distributed system to handle large-scale video processing, decoupling data transfer from computation, and carefully allocating resources, GPUs, network bandwidth, video decoding hardware, keeps things running smoothly. For tokenization, the idea is to convert raw videos into compact tokens. There are continuous tokenizers that produce smooth embeddings, and discrete tokenizers that produce quantized indices. Both approaches help compress the visual data so it's easier to feed large models without losing too much quality. Figure 6 provides a visual representation of this process. Let's talk more about continuous versus discrete tokenizers. Figure 7 shows how continuous tokenizers create latent embeddings with smooth transitions, while discrete tokenizers transform data into quantized tokens. There's a balance between how much you compress and how much detail you keep. Too much compression, and you lose the important bits. The Cosmos Tokenizer is highlighted as a flexible solution. It handles both continuous and discrete tokens, easily taking on various resolutions and aspect ratios. Unlike some other tokenizers, it doesn't rely on a fixed temporal length during inference. Table 4 compares it to others, and the data from MSCOCO and Davis confirms that it's effective for a wide range of image and video tasks. Here we see how continuous and discrete tokenizers stack up in terms of compression rate and reconstruction quality. Look at Figure 8, which shows continuous tokenizers producing smooth representations, and discrete tokenizers focusing on smaller, quantized indices. Cosmos Tokenizer stands out for offering high-quality results with strong compression performance, as proven in tests on the DAVI-IS dataset. Section 4.1 then dives into the Cosmos Tokenizer's architecture. An encoder-decoder setup compresses input frames into tokens using a causal design, where each token depends on current and past frames. This approach cuts out redundant pixels, but holds onto the semantic context needed for tasks like robotics or camera simulation. Let's continue with the encoder-decoder architecture and training strategies for the Cosmos Tokenizer. The encoder uses wavelet transforms and spatiotemporal convolutions to grasp both spatial and temporal patterns. It respects temporal causality, meaning it only looks at what's already happened, not future frames. The decoder follows a similar structure, but swaps downsampling for upsampling. For continuous tokenizers, a simple autoencoder approach maps data into a latent space. Discrete tokenizers add a quantization step for extra compactness. The training procedure alternates between images and videos, starting with a pixel-level loss that measures how well the reconstructed output matches the original input. This helps maintain accurate representations without extra constraints. Here we see how Token Bench helps evaluate and optimize video tokenizers for both images and videos. The framework mixes various loss functions to sharpen reconstruction quality. A perceptual loss checks structural details, while an optical flow loss targets smooth transitions between frames to ensure temporal coherence. There's even a Gram matrix loss that preserves textures. The training data covers many video types, from robotics to driving, underscoring the variety. Meanwhile, compression rates are carefully chosen to balance visual quality against computational effort. This part evaluates the Cosmos Tokenizer across different resolutions and frame rates, looking at metrics like structural similarity and peak signal-to-noise ratio. Discrete tokenizers are also tested at different quantization settings. The results confirm the tokenizer's adaptability to all sorts of video data, preserving quality under various constraints. The new Token Bench benchmark tests how well the tokenizer performs on long-duration, high-resolution videos in domains like driving and robotics. Standard benchmarks like MSCOCO and ImageNet-1K measure image performance. Altogether, Cosmos remains competitive against top tokenizers. Moving on, we compare continuous and discrete tokenizers on popular image benchmarks, MS Coco, ImageNet, and see how Cosmos excels in reconstruction quality. It also does well at different compression rates, measuring results with peak signal-to-noise ratio and structural similarity. The upshot? Cosmos balances quality and compression nicely. Runtime performance is also encouraging, with faster encoding and decoding times and fewer parameters than some competitors. All these metrics underscore Cosmos's efficiency and adaptability for handling a range of data types. Now let's introduce pre-trained World Foundation Models, WFMs. These aim to capture a broad grasp of real-world physics and behaviors. Two model approaches are on the menu: Diffusion and Autoregressive. Diffusion models take a noisy video and denoise it step by step, while autoregressive models predict future frames one token at a time. A handy table here offers a roadmap of these pre-trained models, outlining each version's structure and components. Diffusion-based models feature versions that predict initial visual worlds and then refine them further, guided by user prompts. Autoregressive models focus on token-based future prediction, with specialized decoders and tokenizers. The system harnesses a massive infrastructure, think 10,000 GPUs over 3 months, to power these large-scale generative models, pushing them to excel at visual and temporal predictions. Here, we see how diffusion-based WFMs train in a tokenized space. By reducing video complexity through tokenization, these models more easily generate plausible video frames. The training follows diffusion score matching, where a neural net learns to remove noise from samples. Each noise level is weighted, so extremely noisy samples don't overwhelm the loss. This lets the model hone in on better defined data. The approach also integrates uncertainty-based techniques for multitask learning. Essentially, it sticks to a straightforward denoising objective, which aligns with other known video generation frameworks and stays computationally efficient. Next, let's explore the architecture of the diffusion-based WFM. It starts by tokenizing video frames, injecting Gaussian noise, then denoising them. The denoiser draws inspiration from earlier image generation models that adds special twists for video, such as 3D patchification to handle space and time blocks. Hybrid positional embeddings incorporate both time and space, accommodating varied frame rates and resolutions. Attention mechanisms handle text prompts, and advanced layer normalization fine-tunes the outputs. Altogether, it's a powerful pipeline that turns noisy latent representations into crisp, high-quality video frames. Continuing, we see more about the strategies for training these Cosmos 1.0 diffusion models. Cross-attention weaves text information into the mix, adding an extra channel of context. Attention can become unstable, so they use normalization to keep the model well-balanced. Another optimization reduces parameter counts via adaptive layer normalization plus low-rank approximations. This speeds things up without hurting performance. A neat trick is alternating between images and videos during training, taking advantage of commonalities while still recognizing domain-specific quirks. This approach helps the model adapt to a broad spectrum of data, including different resolutions and aspect ratios, by aligning latent distributions and using relevant condition inputs. Let's shift to efficient training strategies. Normalization keeps signal-to-noise ratios stable as the model scales. Progressive training starts at lower resolution and fewer frames, then gradually ramps up. This spreads out the computational cost while improving video quality. Multi-aspect training puts data into different buckets based on aspect ratio, preserving content alignment. Finally, mixed precision training packs a punch by storing weights in both half and full precision. It cuts back on memory usage and avoids large spikes in the loss. Overall, these techniques combine to ensure a good balance of speed and output quality. Now we look at ways to scale these diffusion models. Text conditioning uses T5 embeddings to tightly link generation to user prompts, so random guidance isn't needed. Video-specific conditioning keeps track of prior frames to maintain temporal coherence. Memory usage is carefully optimized with mixed precision, and activation checkpointing further saves on memory. Fully sharded data parallelism, FSDP, divides model parameters among GPUs to minimize redundant copies. These steps enable large-scale training without crashing hardware, letting the diffusion model produce robust, high-fidelity content. This section explains the computational costs and memory requirements of the Cosmos Diffusion Transformer, especially when handling long contexts. Components like self-attention, cross-attention, and feed-forward layers each contribute to memory use. Activation checkpointing helps by selectively recalculating values on the fly. Context parallelism, CP, addresses the challenge of splitting big input queries and keys across multiple GPUs. An example with the 14B model shows how CP slashes memory from hundreds of gigabytes down to something GPUs can actually handle. They also overlap computation and communication so everything runs efficiently. Here, we compare Cosmos models with other video generation approaches and introduce prompt upscalers. Cosmos 1.0 Diffusion demonstrates high-quality video generation with prompt-aligned details, such as the example of a steam iron smoothing fabric. The 14B model captures motions more precisely than the 7B one, underscoring the advantages of scaling up. Prompt UP samplers further refine the user's text prompts, ensuring more accurate alignment with the model's training distribution and adding layers of visual detail. It helps the model produce more vivid, faithful video outputs. Next, we see some results from Cosmos 1.0 Diffusion generating video based on initial frames, like short 5-second snippets or longer sequences. Check out the examples: a robotic arm carefully handling a wine glass, or an industrial scene with machinery. The 14B model achieves smoother motion and clearer detail than smaller models. Prompt UP samplers also make a difference by matching user queries more precisely to the training data, improving fidelity. The model's ability to handle varying prompt lengths is another plus, showing it can adapt to different user inputs. Now we switch gears to the Autoregressive World Foundation model. This approach treats video generation like language modeling but with visual tokens. After tokenization, a transformer predicts the next token in the sequence by looking at the previous ones. It uses advanced 3D relative position encoding to handle both space and time. The system includes 3D rotary position embedding for smooth changes over time and 3D absolute positional embedding to anchor specific positions, lowering flicker or glitches. Vocabulary management ensures the tokenization fits the model's structure, helping generate high-quality videos. We dive into the Cosmos 1.0 Autoregressive Video 2 World Model Architecture. Input videos become discrete tokens via the Cosmos Tokenizer. These tokens get embeddings for absolute and relative 3D positions to capture spatiotemporal ties. Self-attention and cross-attention layers do the heavy lifting, with cross-attention hooking into text from a pre-trained T5 encoder. Query key normalization stabilizes attention, avoiding gradient blowups or vanishing. A Z-loss penalty reduces extreme output values, ensuring more consistent logits during training. Altogether, these techniques keep the model training on the right track. Next, we see how to scale and optimize memory for these autoregressive WFMs. Large models can gobble up GPU memory with parameters, gradients, optimizer states, and activations. For instance, the Cosmos 1.0 Autoregressive 12B model demands more than 192 gigabytes. Parallelism solutions break the load across GPUs. Tensor parallelism splits the weights, while sequence parallelism divides up the sequence dimension. They even compare other memory-friendly attention approaches from large language models. The training starts with a video prediction task, where the model predicts 16 future frames given a single past frame, gradually scaling from there. Here, we see the nitty-gritty of training and inference. There are two base models, one with 4 billion parameters, another with 12 billion. They're each trained as next video token predictors, gradually adding text conditioning and bridging image-video data. The 4B model focuses on video frame prediction without text, while the 5B version includes text-based prompts. A cooling down phase follows, fine-tuning them with premium data at a reduced learning rate. For inference, the models use large language model strategies, such as tensor parallelism and caching. They also adopt Medusa speculative decoding to speed up token generation without needing extra decoding models. Now let's see how Medusa speculative decoding helps inferences for the autoregressive WFMs. Medusa adds multiple decoding heads, so the model can predict multiple future tokens simultaneously. Only the last two transformer layers and the unembedding layer get fine-tuned for best results. Tests show that 9 decoding heads is the sweet spot, delivering a significant token throughput boost while cutting down on forward passes. To meet real-time needs, they use lower resolutions and retrain the model under these constraints. The discrete video tokenizer is fine-tuned, and the model is retaught with lower-res data, so the Medusa heads still perform well in real-time scenarios. This section shows performance benchmarks and outlines the diffusion decoder architecture. Medusa heads speed up video generation significantly, making it possible to push out 32 frames quickly and hit real-time rates of about 10 frames per second on high-end GPUs. Meanwhile, the Cosmos Tokenizer uses an encoder-decoder scheme to compress data, decreasing tokens at the risk of losing detail. To counter that, a diffusion decoder is fine-tuned for a better balance between compression and quality. In training, the model produces both continuous and discrete video tokens. The discrete tokens guide the denoiser by embedding them in a learnable space, aligning the noisy continuous input with them for top-notch results. Here, we explore the Cosmos Diffusion decoder's training and inference. Videos get tokenized in two ways. Discrete tokens provide guidance, and continuous tokens feed into the diffusion denoiser. During inference, there's a two-step decode. Discrete tokens become a continuous representation, which the decoder then turns into RGB frames. Look at Figure 15 to see the training setup. Notice how both discrete and continuous tokens steer the denoiser. Then Figure 16 demonstrates the inference flow, showing how the decoder leverages these tokens to produce high-quality video frames. Check out Figure 17 for examples from 4B and 12B models in unprompted settings, and 5B and 13B models when they're prompted. Larger models, like 12B and 13B, yield crisper motion and higher visual fidelity than smaller ones. The diffusion decoder does a good job offsetting any compression artifacts introduced by the tokenizer. However, the models sometimes don't improve much with more elaborate prompts, possibly because their pre-training leans heavily on raw video generation. Also, occasional oddities pop up, like random objects that don't belong. It signals where further refinements might help. Now we see performance and some failure cases. Figure 18 shows how the diffusion decoder cleans up blurry outputs while preserving content. Figure 19 highlights examples where models produce unexpected objects, mostly with smaller versions like 4B or 5B under single-frame conditioning. Larger models do better, rarely making such mistakes. The paper emphasizes key evaluation points: 3D consistency and physics adherence. These ensure geometrically plausible, physically accurate simulations, showing how well the model can replicate real-world 3D environments. Moving on, the paper measures 3D consistency in video generation. Smaller models, like 4B, have higher failure rates when conditioned on images. They use static scenes to test geometry. Look at metrics such as the Sampson error to measure alignment with epipolar constraints. They also check view synthesis consistency, where the model generates new camera angles while preserving the underlying 3D structure. By combining these checks, we see where models stand in terms of both geometric accuracy and smooth view generation. Here, the focus is on 3D consistency and physical realism. Cosmos models generally score lower geometric inconsistency and do better at estimating camera poses compared to older baselines. Table 20 shows how they measure up using Sampson error and view synthesis metrics. They also look at physics alignment by running scenarios where objects roll, fall, or balance, aiming to see if the model respects real-world laws like gravity. This type of test is critical for validating that the generated videos aren't just pretty, they behave realistically too. 3 simulated physics scenarios demonstrate the WFM's performance: an object rolling down a slope, objects rolling on a curved surface, and a wobbly stack collapsing. The real simulations show the correct physical behavior, while the model tries to replicate it. Intersection over union, also known as IOU, tracks how closely the WFM's objects match the simulated positions. Results show the models capture a lot of the movement, but can slip up in precision. Perfectly matching real-world physics is tough, hinting at ongoing challenges in bridging the gap between simulation and real-world laws. Next, We look at how the Cosmos models handle physics alignment at different levels: pixel, feature, and object. Pixel-level metrics measure how visually similar the generated frames are to the real thing, while feature-level metrics gauge semantic alignment. Object-level metrics track objects' positions, computing overlaps between predicted and actual locations. Table 20 summarizes these findings. Diffusion-based models excel at pixel level and visual fidelity, and conditioning on more frames increases prediction accuracy. Interestingly, going bigger doesn't always mean better for physics alignment. After a certain point, returns may diminish. This indicates multiple factors matter beyond just model size. Now let's see how Cosmos models move into real-world applications. Post-training adapts them for tasks like navigating 3D worlds, controlling robots, or self-driving. Table 21 sketches out various fine-tuned models. They're proof-of-concept demos, not fully polished systems. Section 6.1 covers camera control. By incorporating camera pose data, the model learns to produce 3D- consistent videos that follow changing viewpoints over time. The training data consists of video clips labeled with camera poses, letting the model predict how the scene should look from different angles. It's a key step in generating dynamic, perspective-aware outputs. Here we continue with camera control fine-tuning. Camera pose data goes into the model as specialized embeddings, capturing how the camera moves relative to scene elements. They also resize input frames and compress them effectively to handle temporal streams. In the evaluation, the model's generated rollouts are tested against real trajectories and frames for video quality and 3D consistency. They measure how accurately the predicted camera paths match the actual ones, checking translations and rotations. It's a thorough test of both geometry and fidelity. Now look at a direct comparison between Cosmos and a baseline called CamCon. They feed each model some starting frames and camera paths, then see how they extend those scenes. The figure uses color-coded lines to show the camera's path over time. CamCon often fails to produce in-distribution futures and skews camera paths, making re-estimating poses difficult. Cosmos, on the other hand, aligns neatly with the input and preserves high-quality frames with a coherent 3D structure. The difference is quite noticeable when you compare the visuals side by side. Quantitatively, Cosmos outperforms CamCon by a large margin in both camera path alignment and video clarity. Re-estimating camera poses becomes more accurate. Cosmos also deals well with scenarios that diverge from its training distribution and generalizes more effectively. It can handle joystick-like inputs, moving the camera around in a way that still looks visually consistent and physically plausible. Next, the paper shifts focus to robotic manipulation tasks. It fine-tunes Cosmos WFMs to predict videos from textual instructions or from specified robotic actions. The Cosmos-1X dataset features humanoid robot tasks, while another dataset supports action-based predictions with continuous video sequences. Check out the results of CosmOS 1.0 Diffusion 7, B-Video 2, World Sample CameraCon under joystick-like controls. They show multiple examples. One is a snowy street view, where the user input guides forward, backward, and rotational movement. Another is an indoor shopping area, with shelves and products shifting realistically as the camera moves. There's also a historical outdoor scene complete with wagons. In all cases, the transitions look smooth, and the scene remains spatially coherent. It demonstrates how well Cosmos adapts to these camera motions. Here, the paper shows how the same input image and control settings can yield different video outputs when seated differently. 3 distinct indoor scenes, kitchen, living room, and bathroom, are used to illustrate how random seeds alter details in the generated video. Even with the changes, the core spatial layout remains coherent. This indicates the model's ability to consistently interpret camera controls while still allowing variations in style or small details. It's a neat glimpse into how generative models can produce multiple plausible futures from the same starting point. Next, we move to fine-tuning for instruction-based video prediction and action-based next frame forecasting. In instruction-based tasks, a text prompt and current video frame guide the model to predict future robot actions. Action-based tasks incorporate data on robotic moves, position, rotation, gripper activity, to foresee the next video frame. Extra cross-attention layers and embeddings adapt the base model for these tasks. Human evaluations compare Cosmos to a baseline using measures like how well it follows instructions or maintains object permanence. The charts show Cosmos outperforming the baseline in both overall accuracy and instruction adherence. Here, we see actual visuals from the model at work. In instruction-based mode, the system might show a robot folding fabric or organizing books as prompted by text commands. In action-based mode, robot movements directly inform the next frame, like picking an item up, then the predicted scene shows that item in the robot's grasp. Both diffusion and autoregressive versions of Cosmos do well, producing outputs that closely track ground truth sequences. Evaluation criteria such as instruction compliance, object permanence, and overall coherence confirm that Cosmos excels over the baseline. Now we get to action-based next frame prediction on a dataset called Bridge, which covers robotic tasks. They measure video quality and alignment with ground truth frames. Cosmos clearly beats the baseline, especially in accuracy and realistic visuals. Then we switch to autonomous driving. The team creates a large dataset called Real Driving Scene, capturing many traffic situations, weather conditions, and road types with 6 camera views. These synchronized multi-camera clips set the stage for realistic driving simulations, whether in busy urban settings or quiet rural roads. Here, the paper talks about fine-tuning Cosmos for multi-view video generation. They produce 3 models that can simultaneously generate 6 camera views. Instead of just scaling up typical positional embeddings, they add unique embeddings for each view, plus text-based conditioning to match the model's perspective to the camera's vantage point. They also add trajectory-based conditioning, which indicates the path, 3D coordinates over time, for the agent. The results show robust generalization to new driving environments, from city streets to riverside roads, while preserving multi-view consistency. Look here at some examples of text-conditioned multi-view outputs. One shows a highway with a truck and a motorcycle, capturing their motion and perspective changes across multiple cameras. Another scenario depicts a multi-car pileup in foggy conditions. The model handles complexity, like reduced visibility and tricky lighting. Metrics like frame consistency and trajectory alignment measure how realistic these multi-view outputs appear. FID scores further confirm that the model's multi-view approach yields believable simulations in challenging settings. This section showcases more text-conditioned outputs from Cosmos 1.0 Diffusion 7 B-Text 2 World. One example features an ice castle with a moonlit background, highlighting refined lighting and textures. Another shows ocean waves crashing against coastal cliffs, capturing believable water dynamics and lush greenery. These outputs remain consistent across multiple viewpoints over about 8 seconds. They evaluate both temporal and cross-view coherence, using Sampson errors to confirm strong alignment. The model edges out simpler baselines, demonstrating better stability and quality. Here, the paper examines geometry and trajectory consistency for multi-view generation, comparing video LDM multiview and CosmosMOS 1.0. They track metrics like trajectory error, how well the generated paths match real-world camera recordings. Cosmos -1.0-TRAJECTORYCOND emerges as the best in accurately following real trajectory data, with minimal translational and rotational errors. They use dynamic mask generation and optimization to get camera poses, normalizing lengths for a fair comparison. The conclusion? Cosmos definitely leads in modeling realistic camera paths across multiple views. Now we see the model's prowess in trajectory condition generation and object tracking. The figure here shows how well the model adheres to user-provided 3D paths, with errors under 7 centimeters from the true track. This detail proves useful for training autonomous driving systems. They also run YOLO V11X on 8-second sequences to test if the model merges distinct objects or does something physically impossible. Out of 157 tracked objects, 0 anomalies were found, signaling strong realism. The section ends by introducing guardrails that block harmful prompts or unsafe outputs, ensuring responsible deployment. Let's talk guardrails. The pre-guard system filters inputs, using keyword blockers to detect unsafe prompts and referencing a database of risky terms. There's also the Aegis guardrail, a specialized content safety model that flags potential problems in areas like violence or criminal planning. If a prompt is deemed unsafe, it gets blocked immediately. Then the postguard system checks the model's outputs. A video content classifier scans the generated frames for potential issues. If any frame is flagged as harmful, the entire video is marked. There's also a face blurring feature to protect privacy. Together, these layers keep the Cosmos WFM system aligned with safe and ethical AI practices. Continuing with the Cosmos safety measures, the paper explains how annotated video data helps train these classifiers. They sample real clips, synthetic model-generated clips, and human-labeled examples to tune the system's accuracy. A lightweight embedding pipeline ensures that if any single frame looks harmful, the video is flagged. Face blurring further ensures anonymity. They also have a red team actively testing the system with adversarial cases. Looking at related work, we see that world models, once rooted in classical physics, have evolved to leverage deep generative AI. This shift opens up new possibilities for richer simulations and better decision-making across countless domains. Now, the paper touches on progress in video generative models, especially text-to-video systems. These breakthroughs enable applications from entertainment to training simulations. Sophisticated models can generate high-res, lifelike videos. Look at Dream Machine or other advanced AI offerings. Two main families of techniques dominate: diffusion models, which excel in visual realism, and autoregressive models, which offer more control and handle multiple inputs. A major hurdle is 3D- consistent video generation, where each viewpoint and frame must remain coherent. But progress in scaling up architectures has reduced reliance on explicit 3D knowledge. Neural networks can now handle camera inputs alone, paving the way for more realistic and flexible video generation. Next, we see how generative models apply to robotics and driving. In robotics, diffusion models help replicate human demonstrations, giving robots a broader learning base. They can also use diverse image and video data to generalize better. This is key for operating in complicated settings. For autonomous driving, video generative models serve as advanced simulators. They can create vast training scenarios with varied maps, weather, or textual prompts, going beyond the usual constraints like sparse real-world data. High-res, multi-view generation fosters realism and consistent driving scenes. Finally, the concept of tokenizers. These compress visuals into simpler chunks, so it's easier for the model to handle them. Both continuous and discrete tokenizers find use in bridging text and visuals for large-scale systems. Wrapping up, the paper reflects on the capabilities and limits of CosmosWorld Foundation models. They hold promise for simulating real-world tasks in robotics, driving, and beyond, but still face challenges like maintaining perfect object permanence or dealing with chaotic dynamic scenes. Human evaluation can be subjective, so more automated tools may help measure true physical realism. They contrast diffusion and autoregressive models. Diffusion models excel at control signals like camera and multi-view generation, while autoregressive models, drawing from language modeling, aim for speed and interactive possibilities. Hybrid strategies are emerging, combining the best of both. Refining these approaches and addressing their current limitations could lead to even more powerful simulation platforms. And that's the grand vision: to keep honing these models, try new hybrids, and push simulation tools forward for future AI breakthroughs. And to you, the hero who made it through this long, deep dive, also known as the ultimate sleep aid, give yourself a high five. You've earned some serious bragging rights. Now go forth, armed with CosmosWorld knowledge, and maybe grab a snack. You've earned it.